And then I just do the same thing for the other components that are present in the reaction. For C7H6, it's just I1 is produced only in the first reaction. C5H12 is produced only in the first reaction. Hydrogen is produced in both the second and third reactions. So it's 7 Zi2 plus Zi3. And the methyl cyclopentane is produced only in the third reaction. So we have it to the extent Zi3. And the total number of gas phase moles here, then we just add them all up. 0.241 plus 6I2 plus I3. And the number of moles of carbon, which is going to be precipitated, is something that you were asked to determine. It's produced only in the second reaction, and its stoichiometric coefficient is 6. So the number of moles of carbon is 6 times whatever we get for Zi2. So mathematically, what we got here is 3 unknowns, as I1, I2, and I3, so we better have 3 independent pieces of information in terms of which to solve for these quantities, and we do. So we just proceed with that. The first piece of information is that the given total pressure at the end is 3.378 bars. So I can write out the total number, use the ideal gas law and write out the expression for the total number of moles of gas. There it is. And that gives me the first equation here, which says 0.572 is equal to 6I2 plus I3. Now, the second relation between Zi2 and Zi3 comes from the given final value of the mole fraction of hydrogen. So I write out the expression for that in terms of the size, and I get for the second relationship what I've shown here, and I see that's fortunately just Zi2 and Zi3, so I have 2 equations and 2 unknowns. At this point, so I might as well solve for both of them, and I do. Here they are. So all I've got left to solve for is Zi3, but in the meantime, I can note that the amount of solid carbon precipitated is going to be my value of Zi2 here. That's number of moles, so I can multiply that by the molecular weight for carbon and get 6.12 grams of carbon precipitated. We have left to solve for Zi1, and that's obtained from knowledge of the mole fraction left of the hexane, 0.063, so I can write out the expression for that, but Zi2 and Zi3 have already been solved for, so I can stick in the numbers and I get this simple equation for which I can solve Zi1, 0.0219. From which now I can reconstruct the expressions for all of the mole fractions in the gas phase of all of the components, and here they are. Any question about this one? So what we ended up here was a system of 3 linear equations and 3 unknowns. And of course you could plug those in to solve in the matrix form if you wanted to do that. I just chunked in solving that as I went along. Yeah?
Could you show where you calculated Zi3? I'm off by a weird amount.
Well, here I just solved the first 2 equations. I solved this equation and this one simultaneously to get those results. So in our next problem, we have gas phase reaction here at 500 K, 4 HCl plus O2 goes to H2O plus 2 chlorine. The system initially contains 5 moles of HCl per mole of O2, and no product species are asked to determine the final composition. So this is like a standard problem. You're told to assume your ideal gas behavior, and that the heat of reaction can be regarded as constant with temperature, both of which are going to be good approximations here. We've got a high temperature and modest pressure, just 2 bar, so we wouldn't even need to be told that that's going to be an ideal gas system. You'd be able to just deduce that. And this is also something which is normally a pretty good approximation. So we just proceed to solve for the standard Gibbs free energy change of reaction and standard heat of reaction in the usual way. So I can write it out for any thermodynamic property change of reaction is always written out here as the sum of stoichiometric coefficients times whatever it is. In this case, it's the formation reactions. So that would be the standard formula for it. The same thing for the heat of reaction. So we just look up on our tables what those numbers are, getting values for the standard gives for energy change of reaction and heat of reaction at the reference temperature of 25 C or 298.2.15 degrees K. So we've got a formula here for calculating then the logarithm of the equilibrium constant at the temperature of interest, and this is a good equation to be aware of. It's just plugging in those values for the standard for energy changes, and that reduces right away to just a number as soon as I plug in the temperature. If I left the temperature unspecified, then I would have the equation for log of K as a function of temperature. But I get 2.300 in this case. So I can exponentiate that to get the equilibrium constant itself as 9.973. Now I can relate that equilibrium constant, thermodynamic equilibrium constant, which is a function only of temperature, over to what I call the stoichiometric equilibrium constant, the one that we express in terms of the continued product of the activities of the participants raised each to their stoichiometric coefficient power, times the pressure raised to an exponent, which is the stoichiometric number for the reaction. So doing that for this reaction is as follows. There's my Ky, and I've got a pressure here of 2 bar. So remember that that's going to be dimensionless because I'm dividing it by my reference pressure of 1 bar. So I've taken care of that. And Ky itself then turns out to be 19.946. Now I've got to do the stoichiometry in order to reduce this to the final composition that I'm interested in. So a standard way that I like to do it is let's take a basis equal to the stoichiometric coefficient here. Well, I didn't. Why did I take that basis? I took a basis of 5 moles of HCl. And then everything is related to that because I've got a ratio, specified a ratio of 5 HCl to every oxygen. That was specified in the problem. So if I think this is 5, then I've got 1 oxygen, no product species, so a total here of 6. Then I can do the usual thing in the table to ultimately get the mole fractions expressed in terms of xi. Put that together for an expression for Ky, which is up here. Solve for the root. I think it doesn't give any problem, but if you accidentally got a couple of roots for it and need to pick, then you'd have to go back and take a look at the limiting reactant and decide what the limits on xi would be. But there was no problem, at least for me, in just popping out the root of 0.811. Then I can go back and solve for the mole fractions from the expressions in this table. This is a standard problem, so I hope everybody's totally on top of this. In the third problem, we have limestone, calcium carbonate, which decomposes on heating to yield quicklime, which is a calcium oxide and carbon dioxide gas. At what temperature does the limestone exert a decomposition pressure of 1 atmosphere? You're told not to assume in this case that delta H, the heat of this reaction, is constant, and then you're given heat capacity constants and other information for the various components that are present in this reaction. So this is our reaction, and I can write down the expression now for log of Kt, the thermodynamic relationship, but now it's this nasty relationship which does not assume that delta H is constant. So the formula that you have written out in your notes is this. This is the log of K298, it's just expressed this way, and then the more general expression for the second term involves these constants that appear with the heat capacities of the components of the participants in the reaction. So we have this delta A, delta B, delta D in this case. So the A, B, and D are given here in this table, so it's just a matter of trying to keep your wits about you and evaluating each of these quantities without making a mistake in arithmetic. You work your way through that, ending up finally with the relationship, let me get finally down to it, that log of Kt is equal to this thing. Any question about how we get to that? It's just kind of a tedious exercise, a lot of places to make little mistakes. Pretty simple in the method. So now what I can do, that's my what I call my thermodynamic evaluation of the K. Now I want to relate that over to the right-hand side of this equation, that is to the activities in the gas phase. Well, this turns out to be almost trivial because in the gas phase, I have only carbon dioxide. It is at a pressure of, so its mole fraction is 1. We're told to assume it's an ideal gas, so that's just 1. And the pressure here is what we're actually after. We want to find out the temperature when the pressure is given as 1 atmosphere, which in terms of bar is 1.0133. So what he got is that K is just equal to 1.0133. So when I take the log of that and equate it to that long expression in T, I get this equation for which I can find the root is 1156.4. Okay. Any question about this one? And if you did it the shorthand way, that is not assuming delta H was, because you had to take the variation of delta H with temperature, you'd get something not too far away from that. Yeah.
Just want to know what's your go-to solver for just finding the root of that?
What I use in Mathematica is find root. So I use find root, plot the function, and then in the curly brackets, I put a guess. I'd say whatever it is, I guess that T is going to be, in this case, I'd say between 500 and 1500, because I know it's going to be somewhere in there. I'm sure there are other ways to do it, but that's how I do it. Anything else? We're going. Okay, the next one is we've got a feed gas to a methanol synthesis reactor. It's composed of 75 mole % hydrogen, 15 mole % carbon monoxide, 5 mole % carbon dioxide, and 5 mole % nitrogen. The system comes to equilibrium at 550 K and 100 bar with respect to these two reactions that are given. The standard for energy changes for these reactions at 550 K, I'm giving you these numbers, and they're already at the right temperature. So we can use those just in a simple way to get values for the equilibrium constants K1 and K2. So you're told to assume ideal gases, determine the composition of this now two-reaction system. So I evaluate the Ks and next obtain the Ky values corresponding to a pressure of 100 bars. So let's look at this first. These Ks that we're interested in, the Kys, I can evaluate first. Those are just going to be a pair of numbers then. So the problem is going to be the stoichiometric side of it. That is putting these activities in terms of the Xis that are involved for these two reactions, and then solve for Xi1 and Xi2 at equilibrium, and then go back and solve for each of the mole fractions. So I took a basis of 1 mole of the feed. You could have taken another basis, but on my basis of 1 mole of feed, I get for all of the initial numbers of moles here what I've listed in this initial inventory. And then in terms of that, I can construct expressions for all of the mole fractions, Y1 through Y6, here they all are, and then put them together in the appropriate expressions for Ky for the first reaction and the second reaction. And that looks like this. So what I end up with are these two equations to be solved simultaneously for Ψ1 and Ψ2. And once I get that, then I can go back and solve for any and all of the mole fractions. And here's a case where it really would be wise to look at the limiting reactants for each reaction and confine your search for this common intersection between these curves in the allowable range. So let's look at that. So the problem is bracketed by determining the allowable range. Looking at the amounts of reactants present initially, we see that the limiting reactant for reaction 1 is carbon monoxide, of which there are 0.15 moles. But the carbon monoxide is also produced in the second reaction to the maximum possible extent of 0.05. So I might actually be able to extend that number so that the upper limit becomes for Xi1 0.2. The limiting reactant for reaction 2 is carbon dioxide. It's present initially at 0.05 moles. So the maximum value of that is 0.05. And there we don't have all the products present for the second reaction, so 0 is the lower limit there. So here are my allowable ranges of Xi1 and Xi2. So I want to confine my search for the common root here of these equations to these ranges. There are different ways to do this. It's a nasty way to do it with Excel. But with Mathematica, you can solve it directly. But I think it's worthwhile to graph it just to see what it is we're looking at. You can use the contour plot function that I suggested to you in lecture just a bit ago. So here is the contour plot over the allowable ranges for Xi1 and Xi2. So we see our solution is here. But if I do it analytically, I get exact results for these solutions, Xi1 and Xi2. In terms of which now I can just go back and construct for all the mole fractions, and there they all are. So any question? Yeah?
When you solve for K1 and K2, you just did like the delta G was R.
Exactly, since I gave you delta G at the right temperature.
Okay.
Yeah, so then it becomes really easy. K is just exponential of minus delta G over RT. And that T is the right T. Yeah. Yeah.
Do you mind explaining again why the upper limit of Psi1 rises to 0.2?
Yeah, let's look at the reactions here. Here, this is my limiting reactant. But you see that I can produce some of it here in the second reaction, so I have to look at the maximum that might be produced in the second reaction and add it to the initial inventory. The first one, yeah. Anything else? Yeah.
Yeah, so in this case, the equilibrium constant for reaction 1 is much smaller than for number 2, but the limit for Xi1 is much larger, or it's just larger than Xi2. I'm wondering if the limits for Xi1 and Xi2 were actually like the same, the upper limits. In a situation where they were the same, would we expect to see a correlation between the largest K value and the largest Xi?
No, I'd have to look at it. If you did see that, it wouldn't be particularly significant. But I don't know the answer. I'd have to look at it.
Okay.
Xi is the extent of reaction, so the bigger K is, the bigger Xi is. That's true if that's what you're asking.
Yeah, it just in this case, the K1 was smaller, a lot smaller than K2, but Xi1 was bigger than Xi2. So it was opposite of what I was
I don't
expecting.
think you would want to mix up the reactions like that. For any given reaction, K and Xi correlate with each other.
Well, not in this case. I mean, in this case, Xi1 was larger than Xi2, but K1 was smaller than K2. See what I'm saying?
I'm not comparing reactions 1 and 2. I'm saying within a given reaction, you have a positive correlation between K and Xi.
Okay.
I'm not using it to compare one reaction to another one.
All right.
Yeah.
How would you at least start with like state this problem in terms of x instead of
In
psi?
terms of what?
X instead of psi.
Yeah, the concept of that, then it becomes tricky because that normally is just for one reaction. So,
You can't do like an x1,
yeah.
x2.
What's that?
You can't do like an x1, x2, like the conversion factor.
You could do it. I wonder if you're specifying a given ratio of components present initially, though, you don't have the liberty of picking a basis to make both sides equal to their corresponding x's.
Okay, so that's x is more useful in.
It's a single
general-
reaction case, yeah.
Single reaction in
Yeah.
general, is
Yeah.
what John has stated, correct?
Yeah.
All right.
You can do a thing like this, just to say it, because the situation often arises where you have a given reaction, the main one you're interested in, and you're interested in that one either giving you a given yield or that it consumes a certain amount of the limiting reactant, same story. And you have so-called side reactions that happen, but you're not particularly interested in those, so you don't bother with the x's in those side reactions. But you look at the main component.
Would it be in that system, you mix in indexes, or are you just?
You just look at the one thing that you're interested in.
Okay. And
Either a
then-
product being produced or a reactant being consumed.
And then your fraction conversion would be off a little bit?
No, no, nothing's off. You just leave X's. Don't try to convert them to X's for anything except that one thing you're interested in.
Okay.
you're not gonna see a problem like that,
Sure.
but in this course, but that's the way it would go. Yeah,
As far as solution method on this one, is it fine if we just took the two, like for this system of two equations, two unknowns, put it into the solver, got two sets of equations and discounted the one that wasn't in the range?
and you ask it again.
Is it, on this one, is it fine if we didn't do it graphically, but?
Oh, of course, this was just to show you.
Okay.
Yeah, I thought it was kind of interesting to look at
Yeah.
graphically, so that's why I did it. No, you could just plug it in and get the numbers. Anything else on this one before we go? Okay, you're asked last year to consider the dimerization of NO2 to N2O4 in accord with this reaction. And you're asked to develop the expression for log K as a function of temperature for this reaction, assuming delta H here again, of the reaction is constant. And to prepare a plot of equilibrium conversion temperature diagram for a system which is initially pure NO2 at a pressure of 2 bar and covering fractional conversions from 0.05 to 0.95. So here's the standard procedure here. We can just write out the expression for log KT. It calls for knowledge of both of these parameters, these Gibbs energy and heat of the standard reaction at the reference temperature. And here are the numbers for that. So I can plug them back into this equation and I get what I'm looking for, namely this. That's what all of these, when you assume that delta H is constant with temperature, the log KT function always looks like this. It's a constant plus another thing over T. And there it is for this particular reaction. So now I can set X equal to xi if I choose the basis equal to the absolute magnitude of the stoichiometric coefficient for the reactant, in which case is NO2, and that stoichiometric coefficient is -2, so it's 2 moles. So we set the basis here at 2 moles of NO2 to start with, no N2O4 to begin with, so I can just do the usual stoichiometric table. There it is, pretty simple. Write down the expression for KY, and then decompose it. The stoichiometric evaluation here is KY times KV. We're taking that as 1, assuming ideal gas behavior. And then we've got the stoichiometric coefficient here is -1. So K is equal to KY times pressure here to the exponent -1. So now I can equate both sides. Log of K is this in terms of temperature. This is now the x's are going to be equal to our x's, as I've indicated down here. So here is my equation for this is my equilibrium conversion temperature equation. And when I plot it up, it looks like the usual form here for, right away we see that it's an exothermic reaction. Okay, any question about this one or any of the homework questions? Yeah,
Can I ask again about like the difference between like the conversion, like the x and the xi? I guess like the xi is like a coordinate, right? Reaction coordinate.
yeah, well, the reaction coordinate is xi.
Yeah.
That's the definition. And we can make X, which is defined as the fractional conversion of a limiting reactant, equal to that if we choose the right basis. And the basis is to take as the initial number of moles of a limiting reactant equal numerically to its stoichiometric coefficient in the reaction statement. So we had 2 NO2, of course, there's only one reactant, so it's the limiting reactant. Its stoichiometric coefficient is -2. So we choose 2 moles to be my initial number of moles, and then xi is equal to x.
And so x is basically xi, but between 0 and 1.
Yes,
Okay.
when you choose the right basis.
Got it. Thank you.
Yeah. Yeah.
So for like 2A plus D, C plus D, would X be equal to 2 xi for that one? Because it's like 2A.
So then you choose, if you've got the reaction as you stated it with 2A, then you choose as your basis 2 moles of A, and then everything else in proportion to that state. And then xi equals x.
Okay, so so you're just using, yeah, so it's just being able to state your inventory, I guess.
Right.
Yeah.
Right. Anything else before we wrap this up? Any questions about anything relevant to the final exam? Once again, it's gonna be next Wednesday, 8:30 in the morning, in here, 1 hour, 50 minutes. Open notes, closed book, and electronics, no electronics. And it's gonna be comprehensive, and there's a draw from material for the whole quarter, but it will be emphasizing this last stuff on reaction equilibrium. Yeah.
So when you're calculating the KY with a nice table, and there are inerts present, you can calculate the mole fraction of the inert, but you don't use that in the KY calculation.
Well, it will be in there because it's gonna affect all the Ys. The inert contributes to the total inventory, total number of moles, so it's in the denominator of every expression for the Y. Of all of the Ys, so it does get in there.
Could, it looks different than that in the notes. I don't know if it's possible. Hold on, it's the notes.
No, it isn't different than that.
Okay.
So,
I believe you.
let's say we had, for this reaction, let's say I had NO2, but I also have some N2 present. And so if I had, and let's say that I have 1 mole of N2 for every 2 moles of NO2. Then that would show up in my table here. I would have then N2 here as well, and that would be 1. This total would then be 3, this is 3 minus I, so I have 3 minus I in each of these denominators, and that would show up in my expression then as I write it out for KY.
Right, you have 1 over 3 minus I,
Mhm.
and then KY would have,
Now you put in these mole fractions, so KY is formulated out of these mole fractions.
yeah,
So
so you have
it's-
y N2O4, and then times N2 over y NO2 squared. And then you have the 1 over 3 minus psi on the far right of that KY equation.
Yeah. It's gonna show up, I believe the difference is just gonna be when you ultimately work it out, that this becomes a 3.
Okay, so it just influences that number.
Yes.
You don't have an additional 1 over 3 minus psi in the KY equation.
I don't have an additional 1 over 3 minus,
So like, on the left side, you have KY, y N2O4 over y NO2 squared. Would you
So
also-
I worked those out, that's why I can put them the way I've got them now. So y N2O4 is gonna be xi over 3 minus xi. And this is now 2, 1 minus xi over 3 minus xi squared.
And you don't.
That will work out to this, now when I've got a 3 there.
Okay.
Yeah,
Is it possible to use a standard state temperature other than 298? So like when we're calculating,
you know, I
KT.
think that is universal. Both sides of the Atlantic use the same one. They use 25C as their reference temperature, and, you know, that's enough for that. We don't have to worry about that one. There is a bit of a worry on the standard pressure, because the older literature uses 1 atmosphere instead of 1 bar.
okay.
Anything else before we go? Okay, what, you sure? All right, what we got left then, we have to have the survey, and Kellen is gonna take care of it for me, because I've gotta get out of the room when we do it.